Okay, so let's take a look at problem 10-12. Let's see, I think I have it pulled up here.
It's
Okay,
on our worksheet as well.
yes, you should have it on your worksheet. I have it on the screen. I'm going to do it right here. You can do it on scratch paper or on your worksheet, wherever you feel like you have enough room for it. Okay. So the first thing we have to do is assess what type of problem it is. And when we read the problem, it becomes pretty clear that it's a buffer system. We're using the disodium form of carbonate, Na2CO3, given the formula mass. And then we're given a particular mass, 5 grams of the monosodium hydrogen carbonate. This is the same chemical system that we looked at actually last class period. That might have been for that problem 10-B. Just a different application of it. But it's a buffer system. We have a weak acid and its conjugate base. And we're trying to produce then a buffer with a pH at 10.00 and a specific volume of that of 100 milliliters. So we know because it's a buffer question, we're going to use the Henderson-Hasselbalch equation. Of course, that equation we all know. We should be able to just write it out. pH is equal to pKa plus the log of base over acid. It gives us in the problem a target pH of 10.00. If we look in the table of pKa values at the end of the text, we're given a pKa of 10.329. We can identify our base and our acid from the problem. And we're given some details about the acid form because we're given a specific mass. So as I was solving the problem, I came through and I just thought, you know what, I'm going to just use the data I'm given and try to take it as far as I can and see if some of these details start helping me figure out what direction to go on the problem. So I just went ahead and I said, well, if I've got 5 grams and it gives me a formula mass, I'm going to solve for how many moles of this I have. It turns out that we have 0.05952 moles of the acid form. And then we're left with a question. How do we figure out the amount of base needed? So what do you guys think we should do here? We've kind of pulled out the information we can from the problem, made some good estimations or guesses as far as what direction we're likely to go with the problem, and done all the calculating we can without maybe some further detail or understanding it completely. So what's the next step?
You could solve for your beta-A ratio.
Yeah, so we could solve for the beta-A ratio, which might be helpful to us. We might find that we do that. As you've seen me do in class, I'll solve something one way once in a while when I haven't looked ahead at it. And I'll realize either, I'll realize it's wrong, or one of you will point out something and we'll realize together, hey, that wasn't done right. And we'll just go back and redo it. Let's give it a shot. So we're going to solve for the ratio B over A. Fill out the Henderson-Hasselbalch equation. This should be something that you've seen done or done now yourself enough times that it's pretty routine for you to calculate that ratio. We end up with 10 to the negative 0.329 is equal to B over A. Solving for that, we end up with a value for that ratio of 0.4688. So when B's concentration is 0.4688, A is equal to 1, right? Remember last time we talked about how these aren't their actual concentrations, but since multiplying 0.4688 by whatever you need to get the real concentration, you would multiply the 1 by the same value. There's a constant that's been removed from the top and the bottom, and it just doesn't matter. The ratio remains the same.
Why would you even care about the ratio? Why would you not just plug in A and find your B.
Plug in the number of moles of A.
Yeah.
Let's see.
You could, I think.
I think you could. That's just not the way that I did it, and that's not the way that Corbin agreed with me to do it. So I think
I just noticed that if that wasn't necessarily the case, it'd probably be easier to just plug something in with the ratio
Yeah.
than have to go back.
no, it
and
looks
read.
like you absolutely could, Brant.
Okay, I was just checking,
Yep.
making sure I wasn't going crazy.
No, well, you might be going crazy, but not evidenced by this particular problem. So there's clearly a few different routes to solve it. This maybe overcomplicates it, but I probably am a little bit prone to going for this ratio and then seeing what I can do with the ratio. You guys have seen me do that a few times. We all kind of fall into our own our modes of operating, and maybe this is one for me, I don't know. But what I did from here then is wrote an expression that helped me understand what those two values mean. And what they mean is that 0.4688 times the number of moles that I solved for above would tell me how many moles of B, and 1 times the number of moles above would tell me how many moles of A, right? Now this is a different application than what we saw before, where we had to add the two values together. And I had to pause while I was solving the problem to think about why that might be the case. But what I realized was that we have two different sources of our carbonate here. So while ultimately our formula concentration is going to equal the 1.4688 coming out of that ratio, we don't yet have all of that in solution. The problem is asking us to add two separate sources of the carbonate in order to achieve one final formula concentration. So that's a significant difference from previous systems where we've started with all of that carbonate, and then we're adjusting it to a specific final pH with maybe strong acid or strong base. And we've been asked to figure out how much to do. So just a different way to think about it. So now what did I do? I used that number of moles. I multiplied by the formula mass. We end up with 2.96 grams of disodium carbonate.